Yes.
Don't forget to record.
Oh, thank you, thank you.
The only thing that matters is the dark here.
Yes, yes, it is enabled. Did anyone look into the homework assignment? Just to get acquainted?
No.
Is it scary? Is it reasonable? Do you find any challenges there?
I was looking at 6 and I just kind of was like, that seems way too easy to other differential, but I haven't actually sat down and done. I just
Oh, the extra credit number 6.
Yep.
Yes, it is one of the standard equations everyone solves in the course of differential equations. Maybe a little challenge only too much initial conditions. But what about number 2 and number 3?
I've only looked at red. I'm not.
So they are challenging. It would take me an hour to do each of them, especially if I'm not prepared. If you would read them ahead, you would appreciate this meeting today. If you didn't, then you don't care. But I hope that the material from today's meeting will be a substantial hint that will shorten possible time waste. Do this work at least twice. So we do have 2 new concepts to learn, and basically today and Friday will be our last time to visit particle in the box. On Friday we will have a ceremony of goodbye party to particle in the box, and on Monday we will start a new subject. So new concepts. 2. One will be literally. Hello, James. Sorry for taking your places.
No, I forgot it when I was late.
That's okay. It's okay. So, concept number 1 will be so-called matrix element, and I'm remembering this concept because I was not a good undergraduate student. I visited maybe 50% of the lectures, which imprinted my future career substantially. But so I missed the lecture matrix element, so I need to learn it through the years on my own. But it really helps to do homework. So basically, one of the homework assignment is to reproduce your results for expectation value of position of the electron inside the box, right? You saw it oscillate, but not from the wall to the wall, but in the middle. And if we try to do it, you need to practice our quantum sandwich. We function, bracket, and operator inside, right? And if I do have a wave function and I do the sandwich at each point of time, I'm wasting my time. Probably, if you would do it on your own, you would figure out how to avoid this waste. Specifically, when you do the sandwich, one can, there was the protocol, the expression that you're processing does include summation of several terms, and each term has factors. Factors that depend on time, factors that depend on space. And if we can separate them, time-dependent factors will evolve and change in time, but space-dependent factors are not going to change in time. Right? So which means we can compute them at the beginning and use them once and forever. So instead of redoing stuff. So basically, this space-dependent factors are called matrix elements of the operator. It's kind of trivial definition, but later on in the discipline, in the courses, and other courses, it is assumed that everyone knows this concept. And if this important little step is missed, I was feeling very badly after missing this lecture, including several other lectures. So we'll go through it. And you see it is kind of self-evident. The second concept is useless for the class because still you are intellectual elite of the globe, but we are just first quantum course. Some of you may decide to take like second, third, so forth. So the next concept that we'll get together, I don't see is useful for little practical purposes of this course, of this course, but it is a solid foundation to those who will move on to a higher order. So this second concept is especially used for those researchers or those people who just study materials who are interested in external perturbation to the chemical molecule or any chemical system, such as whatever you have in NMR, magnetic field, in FTIR, you have infrared electromagnetic field, in UV spectra, you may activate models by laser or by sunlight. Like if external perturbation, most typical, it can be anything, including heat or convolutions, but most typical is electromagnetic radiation. And the concept number 2 is a foundation to describe this type of processes, which will be a little too much for the course, but I just give little, let's say, cornerstones. So when I finish this story in 2 minutes, we will be done. We just need to jump through slides, but they will not communicate anything. So, how many dimensions Schrodinger equation has?
Spatial or 5 or just
Mathematical.
one spatial, one time, so 2 dimensions.
Any other opinions? How many grid points we need to represent wave function? And each of them moves more or less independently. How many grid points? 10, 100, infinity, right? So in some sense, Schrodinger, just one-dimensional wave function is an object with infinite number of degrees of freedom. Because we have height of the wave function at each point, and it is kind of independent variable, right? So it is a infinitely dimensional problem, which is okay. People solve such problems. There are differential equations, there are solutions, but it is, you would agree that infinite number of dimensions is a little discomfort. If one can avoid it, it would serve for the benefits of scientists, engineers, and the whole humankind. Okay? So here is the trick. One can take time independent Schrodinger equation, find eigen states, their functions, right? And then express wave function. I'm putting so much influence and value in my voice that I'm going to say something trivial. Do not expect a dramatic surprise. So one can express wave function as a set of expansion coefficients in front of known wave functions. And number of expansion coefficients, it can be also infinite, but it is countable, right? And if one gets to higher and higher energies, one can vanish the rest, because we never reach in regular chemistry energies of X-ray or whatever. So we can take whatever, 10, 20, 100, no more, right? So discrete basis. And then there is a way to apply the concept from 5 minutes ago, matrix elements to Hamiltonian. So if the operator of total energy, which is a most essential part of the Schrodinger equation, is expressed as matrix elements in the basis of eigenstates of Hamiltonian, it becomes a matrix. And then one can make some manipulations to express the whole Schrodinger equation as a set of matrix equations where expansion coefficients evolve over time. So we assume there is a basis which is not changing in time, but there are expansion coefficients that do change over time, and we write an equation of motion for set of expansion coefficients. So this is this being a Schrodinger equation in the matrix form. So if someone wants to solve it practically, it is very desired form. So, yes?
So basically we're taking equations of motion, solving, like extracting the time dependence out of them and slapping them into a matrix, and that's the Hamiltonian, or is the Hamiltonian separate from those?
Hamiltonian matrix elements govern equation of motion for each expansion coefficient. So if we assume that expansion coefficients are time dependent, then we need equation of motion for each of them. Equation of motion not in a sense of Newtonian mechanics, but equation of motion in mathematical sense. How does the object changes over time?
And in our system, are we just gonna represent that as a vector to make sure we can multiply by matrix? So-
Yes, absolutely. Okay. I had another comment. Yes. Yeah, I'll probably recall it from the slides. I already failed to remember what I was talking about when I started a story about Santa Claus last time. So any questions? Would you agree with the concept more or less? Or discarding it, or need more explanations? Philosophically, not about the technical details. I'm going to show slides and hope you will not fall asleep.
So for the sandwich, is that, so the operator brackets for an expectation on the outside, or do we have just bra and cat on the outside? Or I guess bra and cat,
For matrix element or for discrete Schrodinger equation?
just the sandwich you were talking about? The first one you brought up, is that
So
just,
both, we start with a full wave function as a Bryan cat, but then each full wave function is expanded as a Bryan cat for eigenstates multiplied by expansion coefficient of a certain wave function.
oh, okay, so it's bra, expansion coefficient, cat, and then we have a bunch of those.
Yes.
And the first sandwich was just bra, Hamiltonian, and then cat, sandwich like that. Okay.
Okay.
Might have missed this class.
So feel free to stop me anytime, to protest until I don't believe it. I will think about how to design an interactive style and questions, but right now I don't have a clear idea. Maybe it could be just boring jumps through slides. So here is the homework, and well, find matrix elements. It's literally what we go over here, and yes, find x of t. You have completed it in the lab, right? And reported it as a computational numerical homework, but doing it theoretically is more expensive. And this, you have an idea what to get. This one you haven't done before, so it will be a surprise and most waste of time. Yes, the rest, especially if you do differential equations, like this is trivial, this is middle to high school physics, and this is like very basics of differential equations. I have no doubts that you will do it. But this one is a challenge, just in the remaining 24 hours, 48 hours. Invest 2 or more to focus on it, and not last 2 hours before the class. Okay, so on this diagram, we are returning back to time-dependent Schrodinger equation, but we will do it in a matrix form. And you're so bright that we are 2 lectures ahead compared to previous year. Do not tell to Sam. This is the Bubble software artificial intelligence that reads human prepared image and then reconstructs it based on what it is. I just thought that we all are very bored and we need a little fun. So what do we see here? There is a time dependence of the time-dependent expansion coefficients. We look how they change over time. And this example is when we take into account only 2 eigenstates. One can continue it for like 3, here is a vector of expansion coefficients. There is the vector of expansion coefficients without derivative, and here is the matrix that controls its development, which are matrix elements of the total energy operator. So if you believe into this equation, then you can stand up and yes.
So the 1 and the 2 and the broad ket size, they're corresponding to the wave functions for each expansion coefficient.
You want me to give a comment to your question, which will replace the whole lecture. So if you have m, n, phi m star, phi n, h integral dx, we can shorthand notate it as m h n. Okay, so convolution of wave functions is an operator.
But the index for phi m and phi n are different.
Exact. Generally, two indices. Hello, fine. How are you? Generally, if you speak about square matrices, it is allowed to have different indices. No problem. If you have two, like if you have a free index for expansion coefficients, there is no theorem that they should coincide. We can just do a mathematical experiment and explore what would happen if you have different indices.
Okay, I was just expecting that we would see a wave function and its a wave function and its conjugate with the thing sandwiched in between, as opposed to something else. I guess I should drop it.
No. I see your train of thoughts, and it goes very much. Goes very much just. If you need to broaden our horizons and look onto time-dependent perspective, one cannot. We already went over it. That if there are only eigenstates, there is no dynamics. To have dynamics, we need superposition, we need different states, and we also need non-off-diagonal matrix elements. So it is a key component of the full picture of quantum theory.
So the 1 is just phi sub 1 and 2 is just phi sub 2 here.
Mm-hmm.
Okay.
So, yes. Quantum mechanics for kindergarten. A vector of quantum state on the left and right, factors, matrix, and the full equation. And here is the original stuff that I fed into this machine learning model that you see here. It was designed to draw cats and dogs, and it tries to put an eye everywhere. So this system was trained to draw an object with eyes, ears, legs. So this is the right thing, but I do not like the ugly calligraphy. Yeah, in time. Are you happy with Taylor expansion concept from calculus? Right? So you can represent any function as a summation over some basis sets, such as polynomials of different powers, times expansion coefficient on the front. Right? We can do the same for the wave function, but instead of polynomials, we better take eigenstates. Right? So you see connection. So when we represent a wave function as an expansion coefficient, as expansion coefficients, it is needed when If you speak about an eigenstate, it will be zeros everywhere and one at one place where we have an eigenstate. If you did a superposition as we had in your dynamics example, it will be like square one expansion coefficient, another expansion coefficients for involved eigenstates, and the rest will be zeros. Right? Here is a most non-trivial idea. It's boring and ugly slide, but the rest is quite standard. So the concept of Schrödinger equation in discrete form is needed when we have molecular Hamiltonian that represents how electrons are attracted to ions, and we have eigenstates for, so zero means unperturbed Hamiltonian, but then we have a little addition with the energy of interaction. If you have external electric field that will rotate dipole, or electromagnetic field that will induce dipole to oscillate of low intensity, it is a molecule is still a molecule, but electrons are launched to move a little bit. That creates some superposition, excites from ground to excited, and this is most typical way to think about external perturbation. To have the regular Hamiltonian, which will be diagonal, and then external perturbation, which will be small but off diagonal. So, a little comment to the last question of James. I cannot reproduce his question, but he was a little confused that we have different indices, pairs with different values of indices. Well, when we write down an orthogonality expression, right? When we multiply one wave function by another, we intentionally have wave functions with different numbers, and it will give one if they coincide, zero when they do not coincide. But originally in this procedure, we are feeding in wave functions with different indices, right? So we do not immediately agree that all indices must coincide. A year ago, I thought there was a smart idea here. Now I do not see, and I don't see what is new. So let's keep it. And I will have the same slide with a much better calligraphy. So here we do have a quantum sandwich, right? I would like to attract your attention to this slide because there is a clear motivation. It is a first new concept that is directly related to your homework. So by trying to absorb and discuss and finding rational grain in it, you are helping yourself in completing the coming homework. So when we have time-dependent wave function, and the task is to predict the result of average result of measurement after some time delay, which is most standard problem. We compose a quantum sandwich, which this Dirac notation is replaced by integration. So conjugated, non-conjugated, and operator. Now, in case our bra vector, so it is what we discussed with James before I came to the stage. Bra vector for the overall wave function can be replaced by bra for the first, bra for the second, and in general case it will be series with more and more things. But those are wave functions, and here are expansion coefficients that from now on we believe we start to assume that they are time dependent. Are you okay with them being time dependent or not quite?
Independence just comes from that expansion coefficient, right?
I am asking for forgiveness for going backwards. Just if you get dizzy of quickly flipping slides. Close your eyes backwards. There is a little ugly handwriting thing, but here is your third way to predict future, right? Expansion coefficient at initial time, wave function, and then phase accumulation. So from now on, we combine our expansion coefficient at 0 time and phase accumulation into one object, time-dependent expansion coefficients, each of which accumulates phase according to the eigenenergy of a given eigenstate. Okay? So it is what is assumed as C sub n depending on t in what follows. Good? We check forward. Now, ket vector. We have a ket for the first state, ket for the second state, and expansion coefficients which are time dependent. Bracket. And an operator in between. So now I'm going to do nothing but just opening the brackets. If we have 2 terms times 1 terms times 2 terms, 2 times 2 will be 4. Right? So there should be 4 terms. So E1 star, E1 without star. Ra 1 operator get 1. Right? So we take first term in the each of expansions and compose for first term in the answer, right? And just slightly reorder the factors so that the first factor will include everything that relates to time evolution. And second one, everything that is related to convolution of the wave functions with an operator, right? And this notation here means phi 1 star times a times phi 1 without star dx from minus infinity to plus infinity. Okay? And then if we keep opening the brackets, it will be same style of terms, but indices will be different. 1 and 2, 1 and 2. So indices coincide in time dependent and spatial parts. 2 and 1, 2 and 1, 2, 2, 2, 2. Right? So we need to build this convolution of the eigenfunctions with an operator only once for as many states as many are involved in the dynamics. But we do not need to redo it again and again. Like if you literally follow the first line, it means we take away function and find convolution, take away function and find convolution. But if you try to do it, you will recognize that we are doing some silly job. There should be a way to simplify. Okay, and those objects are called matrix elements, right?
Right.
Yes.
Yeah.
We have generous 18 minutes. Not 18. 27. No. 17. We need to finish at 50. Still good. Matrix element. So if a stranger in a store asks you what is matrix element, you probably will not answer with a well-made sentence. You know, it's an object making together stuff with star and without star, and we use it once and forever, right? You should be able to do it. So you got the concept. We may design a quiz when everyone will try to define matrix element by personal words. Sometimes it should be a little fun. Okay. And since there are 2 independent indices, those objects can be arranged in a matrix. Therefore, it's called matrix element. So any operator can be represented by a square matrix if you have chosen a basis. And we were referring to it in ambiguous way before, but it is exactly why Dirac notation is introduced. So an operator can be represented either as differential operator or a matrix, but they represent the same essence, the same processes, the same properties. It just glance from different angles. Okay, so expectation value is time-dependent wave function, time-dependent wave function, and matrix in between, and then we get the same answer, right? So row by matrix by column, and then we get a number, and this number will be the expectation value of an operator along a trajectory. Now we do have a connection. We need to find an equation of motion for this expansion coefficients. And this is a very trivial task. Before we already agreed that the C sub n of t will be equal to C sub n of 0 times E minus I over H bar E n t, right? Right? But there are situations when external perturbations, which are time dependent, and the Hamiltonian becomes mathematically not easy to diagonalize. So inside this approach is designed for such situations where eigenvalues are hard to find. And then one needs to design something more general to find an answer for expansion coefficients as function of time. Again, this goes a little beyond the scope of this course, but it is an important foundation. Okay. There is a little thing that I tend to skip because of the lack of time, but there is an alternative form of discussing quantum dynamics where one deals not with expansion coefficients, but with density metrics. So we briefly introduced it, right? Pairs of expansion coefficients. There is a mathematical operation of trace. So if you did some advanced linear algebra, it's just adding summation of the diagonal elements. So if one is doing a product of density matrix times matrix element for a given operator and then practices a trace, it will give the same answer here as in our standard sandwich. So a way to find an expectation value of observable is to multiply density matrix by matrix of matrix elements and take a trace. We are there to go to graduate school and join the group, which we will main to do research. Okay, so continuing. There is a orthogonality property for good basis, and we are going to use it to derive Schrodinger equation in discrete basis. So here is our most standard Schrodinger time-dependent Schrodinger equation. Here is our expansion of a function over a basis. So we now plug in 2 into 1, right? Yes. So after we plug 2 into 1, Hamiltonian times wave function is there. So we do not use matrix notations yet. But you believe this step, plugging in is harmless. Isn't it? So now we can do the following trick: multiply from the left by a bra vector with an arbitrary index m. Can you? If you're in doubt, let me know. Okay. Mathematically, we have mathematical liberty. We can multiply anything by a same factor from left and right of the equality sign, and it will be still equal, right? So now we have m red m everywhere here, and see what we've got. So time derivative expansion coefficient, and then sandwich m bra and ket 1, m bra and ket 2. Here again sandwich m bra and ket 1, expansion coefficient outside, and here we have the Hamiltonian inside this sandwich, right? Hamiltonian inside the sandwich. We function here with basis states, brackets are assumed as time independent, right? It is what we agreed on. Those are solutions of time independent Schrodinger equation. They do not depend on time. Yes? So then time derivative can be placed outside of this, and expansion coefficient can be also placed outside of this. So we will have only convolution of arbitrary wave function m and wave function 1. Same here, arbitrary wave function m and wave function 2. What do we expect them to be simplified into due to orthogonality? A sandwich of two wave functions, 0 or 1, depending on whether these indices coincide or diverge, right? Okay, and here we have just matrix elements of Hamiltonian. Right? I don't know how to make this step more entertainable. The only comforting fact that we need to suffer only 9 minutes and then we will be over. So let's plug the specific values of m, 1 and 2. So if m equals 1, this convolution will be 1, this convolution will be 0, right? It is what Spencer helped me to think, right? If m will be equals 2, this will be 0, this will be 1. And now we can rewrite the equation from previous slide 2 times. Once when m equals 1, another one when m equals 0. So look here what we have. So if m equals 1, coefficient in front or behind C1 becomes 1, coefficient behind C2 becomes 0, right? So when m equals 2, coefficient behind C1 is 0, behind C1 is 1. So this trick parses only one and expansion coefficient out of the long series, right? And then stuff is not the only changed things that we do have. One here and two there because of our original statements, right? Time to protest or stay muted forever. Does it look reasonable? Do you see a little motivation why we should get through it? Right? So our goal is to have Schrodinger equation in discrete form. And now we do have 2, implying that we have more discrete equations. So first equation is for time dependence of C1, which depends on C1 and C2. Right? And then the second equation for C2, which depends on C1 and C2. So it's a coupled system of ordinary linear differential equations with constant coefficients. They're not independent, they're coupled to each other, right? Because it this through C2 it couples to a second equation, this through C1 couples to the first equation. So can we rewrite it in this shape? So C1 will be equal rho by column H11 times C1, H12 times C2. I'm going to scroll back and double check it. So what an equation disappeared. Oh, yes, just here. So time dependence of C11 is H11 times C1 plus H12 times C2, right? So it is the same what we've got from row by column rule. If we need an equation of motion for C2, we do row by column H21 times C1, H22 times C2. Right? So by the shape, by the structure of this equation, it is not continuous anymore, right? We do not have derivatives except time. We don't have differential operators in respect to space. So if a good colleague gave us, or a computer gave us eigenstates, and then we do have this and matrix elements of Hamiltonian, we can solve for wave function expansion over time without dealing with multi-dimensional calculus, right? So it is if we have a good colleague who will always provide us with eigenstates, we can like cross through, remove multi-dimensional calculus and partial differential equations from our curriculum. Which is not, I'm not telling that if you plan to, you need to, but it gives us a little excuse to make the life simpler. Okay, so just keep linear algebra. Okay, and I don't know what else. It should be above the last slide. Yes. Please, on my behalf, symbolize the end of the meeting. Everyone is welcome to depart, disconnect. Hey. Yeah. Yes. Meeting is done. Adjourn is announced. Yeah, feel free to depart. I'll stay here to answer any questions. I'm looking forward to see you in the. So today we will start a very new piece of software which we will be practicing for the rest of the class. It will be a basis for your independent projects. Exciting.